In section 16.6, we want to look at some applications of double and triple integrals beyond the area and volume that we've been doing. In particular, we want to look at the moment and center of mass. So if we've seen that it's possible to find the mass of an object by integrating a density function. So we could have the mass of a lamina. A lamina is a word for a two-dimensional region, right? So this would be your lamina R, where this is your x-axis and this is your y-axis. And if we want to find the mass, we would have a density function, right? So there's some density of this lamina. Lamina is a fancy name for like a plate, right? So imagine it's like a plate, right? So we have the density function, and we would integrate it over the two-dimensional region because, of course, it's flat, right? It's a flat plate. We could also find the mass of a solid, right? If we have some three-dimensional item, right? Three-dimensional solid, right? That would be solid D. And then we could find the mass of that solid by, if we have the density of that solid, then we take the triple integral over the volume. Right, so we have seen both of those before. Actually, we haven't really seen the mass of a lamina. That's a new word, but nevertheless, we've seen R as the region. And then we also have the solid D. Okay, so let's think about a moment. So in one dimension, when you're in physics class, you may have learned that the moment is the tendency of a mass to rotate around a fulcrum or a fixed point. So you have your fulcrum, right, which in math we would generally establish at x equals 0 because that's the way we think about this. And then we have our mass over here. And then here's your value x. And so the moment in the x direction is mass times distance, or mx, right? M times x. That's multiplication. Now in two dimensions, it's going to get trickier, right? So one dimension moments are easy, but in two dimensions, the moment is the tendency of the mass to rotate around an axis. We generally have two standard moments. You have your moment in your x direction, which is the tendency for it to rotate around the x-axis. Then you have your moment in your y dimension, your tendency to rotate around the y-axis. Okay, so let's see what we're talking about here. So we have some lamina. We have an x-axis and a y-axis, right? And then we have this lamina, this region, right? There's your lamina. And so we think about a section of this, right? Just a piece of it, right? The area is dA, right? And remember, then we stack a whole bunch of these in, and there we have it. So the tendency, the distance to the y-axis is over here. Because you might have noticed that in here we have x in the my. Why is that? Well, because the distance of this little section to the y-axis, that it's the tendency to rotate around this y-axis, right? You're trying to think about it going here. That tendency relates to the distance to the y-axis, right? That's why x is in there. It's right. So it's x times the density. And then you integrate it. And then your distance to your x-axis is y, which is right here, which is why there's a y in mx, because y is the distance to the x-axis. So just like it was in a single dimension, your moment in the x direction is mass times distance. It's just that it's a little bit trickier to find, right? So mass is actually the double integral. Let me write it this way. Mass is the double integral over the region of your density function, which is a function of x and y, dA. Right? So that would be your mass, right? This finds, right, when we integrate density, we find mass. times that distance, which was y. And then putting that all together, we have the formula written up above, right? You take the double integral over the region of y times your delta function, your density function, dA. Right? So this is mx now. So in one dimension, it's this. In two dimensions, it's this. And obviously the other one works similarly. I'm not going to derive that. So now you're probably guessing, what about three dimensions? Yes, exactly. So then in three dimensions, how does that work? Okay, so you imagine you have some solid, right? Something with some kind of depth. So here's your solid D. And you have, instead of a square, it's a cube, right? dV, right, is the volume. All right. Then we have density, which is delta of x, y, z. So there's our density function. And then I'm just going to show one of these, but they all work very similarly. So just trust me on this. All right. So this distance from this little cube down to the xy plane, right? So here's the xy plane, is z, right? So this is the distance to the xy plane. Because that's what we're figuring out. When we have a moment, it's the moment about the xy plane. Okay, so z is that distance. So then the moment for xy is mass times distance still. But mass we find with now the triple integral over the solid of the density function for that volume, right? So it's volume times density, if you will, times the distance, which we found, which was z. Rewriting all of that, mxy is, and this is three-dimensional that I'm doing, is the triple integral over the solid of z times delta xyz dv. Oh, and in case this wasn't clear, the reason this is happening is mass is volume times density, right, roughly. But of course it's varying, so we have to use calculus to find it. We have to use integration. We can't just use multiplication. Similarly, on the previous one, when we did it, oh, hold on, I lost my page. Here it is. This one. So the reason this is happening is mass in this case is density times area, because this is only a two-dimensional thing. So it didn't have a volume because it's a flat plate. So it has no volume, it only has area. So you take density times area, and of course you have to do it with integrals because this is not a set thing. These aren't constants. If they were constants, that would be easy to do. But usually they're not. Usually the density varies. It's denser over here than it is over here or whatever. And the area is certainly not a nice, easy area to do. It's not a rectangle. So because of both of those reasons, we have an integral to do this, right, to do that multiplication. Same thing here. This is denser on one side than another, or denser up on the top than it is on the bottom, or whatever. And the volume is not a nice, easy thing. This is not a nice, easy object to find the volume of. This is not simple geometry. It's more complicated, and therefore we need the triple integral to do it. All right, one important use of moments. So moments are these tendencies to rotate around around a distance from a point, around the x-axis or y-axis, or around a particular plane, right? So these were the different planes. So we had z here, we have y here, we have x here, depending on which plane you're looking at. And then for these ones, it was around the x or y axis. So that's what moments are, right? It's the tendency to rotate around a particular point in one dimension, axis in two dimensions, or plane in three dimensions. So one of the best applications for that, for those moments, is to be able to find the center of mass, which would be the balance point where you could get it to balance. So if you have a lamina, if you have some two-dimensional plate, right, then the spot where it would balance is x bar, y bar. If you've ever taken a statistics class, you've learned that the bar, the flat bar on top of the head like that, for x or y, means the mean, right? It means the average, which in our application would be the center of mass, right? The center of the x's, then the center of the y's. And then in a three-dimensional object, right, it'd be some object, right? And then the center of mass for that object, which would be where it would balance. This is very important, of course, for gymnasts and things like that, right? Gymnasts have a center of mass upon, and where it is really affects how they're able to tumble, which of course is one of the reasons that gymnasts are short, right? Gymnasts and figure skaters, especially female figure skaters, tend to be on the short side because their center of mass is lower than, right? Also because they can fit the equipment better. Now, before we go tackle a problem that uses these, I'm just going to give you a warning. There are a lot of calculations. So this is really a warning. There are a lot of calculations that go into finding a center of mass. It's going to take a lot of work. These problems are going to take a lot of paper. But we often use symmetry, very often, use symmetry to reduce the number of coordinates, right? Symmetry will really help, right? Symmetry helps. Also, always make sure that, I'm just going to make this, make sure that you use the same limits of integration. Always use the same limits of integration for all the integrals. That'll mean something to you in the next video when I show you an example. But this video is getting too long, so I don't want to put it in here.